What's going on, Science 10s? Mr. Walton here. Hope you're having a good day. In this lesson, we're going to be learning about the theory of spontaneous generation. Now, it was first proposed by the Greek philosopher Aristotle around 350 BC. So what that means is that this idea has been around for thousands of years. It's the idea that life can emerge spontaneously from a non-living matter. I'll give you a couple examples about that. Before we jump into the examples, I just want to say that in order for you to really understand the theory of spontaneous generation, you have to kind of put yourself in the shoes of somebody who doesn't know about the microscopic world. They don't know about bacteria. They don't know about life that's smaller than what you can see with your own eyes, okay? You also have to kind of ignore some of the things you intuitively know, like all life emerges from something, like all life is hereditary. You pass on traits to your children and things like that, because those kinds of ideas weren't really concretely thought about or proposed until much, much, much later. So the first example of spontaneous generation is kind of a recipe for mice. This is just a little bit of a joke, but if you had, some old clothes and you had a little bit of food left in those old clothes, that if you gave it time and you came back a little while later, you would see mice in that pile of old clothes. And so it was a very rational thing, if you didn't know any better, it was a very rational thing to just say, oh, well, the shirts aren't alive, and the wheat, as much as the wheat comes from something that used to be living, it's not physically alive right now. It's not moving around a lot like the mice is. And so from these things, if you give it a little bit of time, that life will just spontaneously emerge. It's just at the behest of the universe, something living will come out of that. Another example, and I purposely didn't include some pictures here because I know it can make people a little bit queasy. They're kind of uneasy with the idea of this, but that's okay. So if you take certain types of food, specifically meat, if you take some form of meat, and this is just like salmon or whatever, and you give it a little bit of time, it's going to start to spoil or it's going to go rotten. And if you give it enough time, you just kind of leave it out in the open, you eventually will see maggots forming. Now, we know, hopefully, what maggots are, and maggots are the larva stage of a fly's life cycle. But people didn't know that back at the time, okay? People's understanding of things was largely... People's understanding was largely based off of what they could observe about the universe or what other people have observed about the universe. And the idea that maggots coming from flies hadn't necessarily been observed yet. So we're going to talk about 3 experiments that were really crucially important in being able to refute the ideas of spontaneous generation. And the idea of the microscope is going to become really important here in a little bit in the third experiment. So in 1668, an Italian physician or doctor and biologist Francesco Redi wanted to know if maggots that formed from rotting meat were truly as a result of spontaneous generation. So he performed the following experiment. He had 3 beakers. He actually had 6, but that's okay, whatever. It's not that big of a deal. He had 3 beakers, and he put various types of meat, in the 3 beakers. And now remember, he had 6 beakers, so he was using the same types of meat over and over and over again, but he wanted to test different meats. In our picture, it's just a little bit of a simplification. So in our simplified version of Redi's experiment, we put meat in 3 different jars or 3 different beakers, and then we covered them with 3 different things. Now, as long as the meat was fresh when we first put them in the jars, they hadn't started rotting yet, then they wouldn't have come into contact with anything else that was really necessarily living. So what he found was when he left the meat in the completely open jar, there's no lid on the jar at all, that the flies would gather around the jar, and that eventually, given a little bit of time, maggots would form on that meat. Okay. He completely covered another jar, put fresh meat inside, and completely covered another jar. And so the flies weren't necessarily attracted to this jar because they couldn't, sense what was going on inside the jar. They weren't necessarily attracted to any scents or anything like that. So the flies didn't conglomerate around it. But most importantly, the maggots didn't spontaneously form on the meat. Okay, that's quite interesting. He performed a third experiment with a third jar where he took a fresh piece of meat and he covered it in something called cheesecloth. Okay, so in the first one, there was no lid or no cover, right? In the second one, there was a lid, and in the last one, there's something called cheesecloth. I don't know if there's an E on the end, but that's okay. Whatever, it's not that big of a deal. So cheesecloth. What that means, cheesecloth is a porous material. It's a lot like a filter, okay? So this cheesecloth allows air to pass through it, but it doesn't allow larger things, particularly like flies. And so what he found is that the flies would conglomerate, or they would gather around the beaker with the cheesecloth, but they wouldn't be able to come into contact. And he also observed that after a little bit of time, no maggots formed on the meat. Now, in all three cases, the meat spoiled still. Yes, it still rotted. But the meat did not form maggots in the two jars where there was some sort of a cover. There was a barrier between the meat and the flies. So what did he do? He set up 3 jars. Remember, this is a simplification. So 1 with no lid, 1 with a lid, and then 1 with cheesecloth. I'm going to use no E here just to hit both. I don't know if it's correct, whatever. And so his results, what he found, his observations, is that only the jar with fly access to the meat formed maggots. And he was pretty certain that this was quite, solid evidence to kind of refute the idea of spontaneous generation. So what we're going to do is we're going to go through this experiment. We're going to kind of define some things. So just bear with me for a second. So there were some variables in Reddy's experiment. Now, remember, a manipulated variable is the thing that you're changing through the different trials, okay? So it's the variable that you choose to change. That's what a manipulated variable is. The responding variable is the variable that results from your change. So you can think of it as, what are you measuring? What's the outcome of the experiment? And then the controlled variables are all variables that you choose to hold constant through the entire experiment. So when we go back and we look at what's going on, when we go back and we look at the experiment, well, what's the one thing that's changing across these three trials when we go here? No lid, lid, and cheesecloth. It looks like the type of covering on the jar. So when we go back to define that, the manipulated variable is going to be the type of cover on the jar or the container. The responding variable, well, what was the measurement that we were choosing in this experiment? Well, the responding variable was going to be whether or not maggots formed. And that was either like a yes or a no. That was our measurement. Now, controlled variables are all of the variables that you're choosing to hold constant over the entire activity or the entire experiment. So all the things that you could have changed but chose not to. And so typically that would be like temperature. You don't want to have one piece of meat in the freezer and have one piece of meat, out in the sun all day, something like that. Another one would be the type of meat. Another one would be whether or not they were kind of in the same location. Things like that. So all of these were really important in holding constant because in any experiment, you should only ever change one variable. There should only ever be one manipulated variable. So you want to see, does the manipulated variable have an effect on the responding variable? And if there's no real change across all three trials or across our trials, then you can conclude that there should have been no effect between the manipulated variable and the responding variable. So what were the observations here? Well, the observations were if flies had access to the meat, then maggots formed. It doesn't have to be any more complicated than that. In the jars that were open, or in the jar that was open, then the maggots formed. But in the jar that wasn't open, then the maggots did not form. So the conclusion that we're going to make is spontaneous generation is not supported because the beakers or the jars with lids or coverings or whatever, the covers did not grow maggots. Perfect. Okay. So Reddy did his experiment in the late 1600s, and then in the early 1700s or mid 1700s, there was still a consensus in the scientific community that no, we're still really happy with this idea of spontaneous generation. So despite the evidence collected by Reddy, many people still believed in the ideas of spontaneous generation. In 1748, John Needham, he was an English individual, he conducted an experiment where he boiled samples of chicken broth to try and support the idea of spontaneous generation. So here's what he did. He boiled some gravy or some broth, okay? It's kind of, they're synonymous with each other a little bit. So he boiled some gravy or some broth, and he left the flask open to the air. And so what he did was, when he boiled the gravy or the broth, that he was very happy that he was killing any microorganisms that would be living in the broth at the time. And that when he left the flask for, a day or 2 days or several days, that the gravy or the broth would be teeming with microorganisms that he could see on his kind of new microscope at the time. And so he thought, okay, all right. So we're killing everything in here, and then we're leaving it for a little bit of time. And after time, right, life is going to begin again after a certain amount of time. So this idea, his conclusion was that it supports spontaneous generation. But it also brought out this idea of a vital force in the air. Or you can think of it as like a life force. There was a life force that was required for this to be able to occur. So, unfortunately, there were some problems with Needham's experiment. And this was kind of pointed out by an individual, Lazzaro Spallanzani, who was another Italian researcher, a chemist. So he pointed out that in this experiment, John Needham didn't boil the gravy for a long enough time. He only boiled it for 15 minutes. And in his experiments, that when you boiled the gravy for only 15 minutes, that microorganisms would always form no matter what. So he kind of pointed out that, well, this isn't enough time. So what he did was he boiled the broth for 1 hour, for an entire hour. And he found that did, in fact, kill all of the microorganisms in the broth instead of just the 15 minutes. What he also did is he sealed the flask after boiling. And so what he did was he tried to kind of separate the newly kind of what we would say is sanitized or pasteurized, right, broth from anything else in the environment that could contaminate it. So he boiled it for an hour, he sealed the flask, and the gravy or the broth was free of microorganisms. But this was just a little bit more support for the vital force. So critics of this experiment said that, well, this flask isn't open to the air. You've killed the vital force. You've destroyed the vital force or the life force in the air at the time. And so because no air can get in here, that no vital force could cause life to be able to spontaneously generate. So now it took almost 100 years for an individual to come along and be able to really kind of settle the debate. So in 1864, a French chemist, Louis Pasteur, who most people should recognize that name, repeated the experiments by Needham and Spallanzani, but with a slight modification. As a result of the work done on microscopes in the past, Pasteur was worried that there could be organisms in the air or on dust particles that were so small that they couldn't be observed with the eye. And so what he was worried about, what Pasteur was worried about, was that when this flask is open to the air, yeah, sure, a life force can get in there, right? So air can get in here, but also Pasteur is worried that any sort of dust can get in there. And on the dust would be these microorganisms or these bacteria, and they would start to grow once the dust came into contact with the broth. So Pasteur was worried that there could be organisms in the air or on dust particles that were so small they couldn't be observed with the eye. He designed a flask that would be open to the air, but would not let dust particles settle into the liquid contained within the flask. And so that's exactly what he did. So he took a flask, and the idea is that we have a swan neck flask. So the swan neck flask here is this flask, and it's got a neck on the flask. It's a long tube that was bent into this S shape. And so what happened was he would boil the broth for an hour, and he would kill any of the microorganisms living in there. But any of the dust, right, that would come into here would settle in the bend of the tube. The dust had no, because there's no airflow coming in, air has access to it. Like, don't get me wrong, this is open at the end, so there's air that could come in here, but there's no real flow of air that's strong enough to bring these dust particles in. And so the dust particles would just settle at the S curve, at the bottom of the curve of this flask. And so if it doesn't matter how long you wait, there was no growth of microorganisms. And in fact, still to this day, like this experiment was done in the kind of mid to late 1800s, still to this day, the original swan neck flask that Louis Pasteur used is actually on display in the Pasteur Museum. And so you can go to this museum in France and you can look at this flask, the flask with a really long S-shaped neck. And this flask has been sitting for over 150 years. It's got broth inside of it, right? This broth should be totally disgusting and gross. But because no microorganisms have access to it, any dust just falls and settles at the S bend in the neck. And so still to this day, that broth has not spoiled. It does not have any microorganisms living in it. So the swan neck flask was critical. Now he did the same experiment with a straight neck flasks, a lot like Needham and Spallanzani did. And when he used the straight neck flasks, then the dust, the settling into the liquid brought with it microorganisms, and so the food spoiled. What he also did was he would boil the broth with the exact same type of swan neck flask, and he would let it sit, and there would be no growth for as long as it had the swan neck flask on it, or the swan neck on it. But he would break the flask, and a few days after breaking the flask, that's when he saw the growth on it. And so he had swan neck flasks. He had swan neck flasks that were broken. So he had broken neck flasks, and he had straight neck flasks. And the swan neck flasks produced no microbial growth. The broken neck flasks did, and the straight neck flasks did as well. So when we look at our variables here for this, the manipulated variable, well, again, that's the thing he was intentionally changing, right? So the manipulated variable is the neck, the type of neck on the flask. The responding variable was whether or not there was microbial growth. Again, it's more of a yes/no question. All the controlled variables. Well, the time. Remember, that was kind of one of the big things that was missing in Needham's experiment. So the time taken to boil, also the temperature, right? The type of broth, all those sorts of things. The observations. Only the Swan Neck flasks avoided microbial growth. So the conclusion, right? We haven't made any inference about this yet. The conclusion is that the dust settling in the neck of the flask must contain microbes that cause growth, not spontaneous generation. And I will have to say, I should have said this earlier, that these Swan Neck flasks, they would stay totally fine, not spoiled, no growth, for as long as the neck stayed intact. But also, what he would do is he would tilt this. So he would take this flask and he would rotate it so that the liquid, right, kind of like that. Oh, that's terrible. But that the liquid could flow down into this bend, and then he would tilt it back. And as soon as he did that, then he started seeing microbial growth. So it was the interaction between the liquid here and the dust particles in the Swan Neck flask. So hopefully that makes sense. Hopefully you can take away that with proper experimentation, you can either support your ideas or you can refute ideas. And so this idea of Louis Pasteur's Swan Neck flask really was the nail in the coffin that refuted the idea of spontaneous generation. I mean, you can't argue that the air had access to this flask. So this air had access to the flask, so the vital force of the life force had access to the broth, but it's been 150 years now, and nothing has grown in that flask, right? So there had to have been something else in the works. So that's it for the lesson. Hopefully you learned something new. Tomorrow we're going to be taking a look at some more evidence of discoveries made by microscopes over the last couple hundred years. So have a great day, and we'll see you tomorrow.